In solving stoichiometry problems, there are three parts to basic stoichiometry. One, chemical equations must be balanced. That's why we spend a lot of time learning to balance chemical equations. Two, the coefficients in a chemical equation represent the smallest whole number ratio of moles. Remember, we use moles because atoms are really, really small. And we use this thing called a mole ratio as a conversion factor between moles of a known substance to moles of an unknown substance. It can be found using the coefficients in an equation since the coefficients represent the moles. So our conversion factor from getting from the known to the unknown is the coefficient of the known with the unit of moles on the bottom, and the top of our conversion factor is the coefficient of the unknown with the unit of mole. So we could take a look at a balanced chemical equation such as the one on the previous page and develop some different mole ratios based on the coefficients. So if we highlight N2 in this pink color, H2 in this blue color, and NH3 in this purple color, let's see how we can develop different mole ratios. We see that 1 mole of N2 is equal to 3 moles of H2, so I could say 1 mole of N2 over 3 moles of H2. I could also flip that. I could say 3 moles of H2 over 1 mole of N2. I can say that for every 3 moles of H2, I have 2 moles of NH3, so I could put 3 moles of H2 over 2 moles of NH3. I could also say that in order to make 2 moles of NH3, I need 1 mole of N2. So you can see there's lots of different possible mole ratios we can develop, and we've only shown 3 here. And remember, all conversion factors can be flipped or switched around based on what your known quantity is and the unknown quantity that you're trying to find. So let's take a look at a possible problem. How many moles of N2 reacted if 2.53 moles of NH3 is formed? First, we need to identify what we're given in this problem. Again, it's the same as the number with the unit, so we see 2.53 moles of NH3, so that's our given. Our unknown in this problem is moles of N2, so I am going to identify that as my unknown. So you can see we're not even dealing with H2 in this problem, and that is going to happen. You will only ever deal with 2 substances in any stoichiometry problem. A good practice in stoichiometry, just like the mole, is to identify the pathway we're going to take. For all of these problems today, we are only going from mole to mole. So we're going to go from our mole of our known, which can also be identified as the given, to the unknown, so the number of moles of the unknown. So we start by setting up our problem with our given, which is our 2.53 moles of NH3. As we're going from mole to mole, we are only using the mole ratio. So here's what it looks like again, and we're just going to fill in our known and unknown over the top of our mole ratio that we have. So our known is our NH3, so the coefficient on NH3 is 2. So I have 2 moles of NH3. On the top, I'm going to put my coefficient with my unknown moles. So that is going to be my 1 mole of N2. And our math is the same as always. 2.53 times the 1 divided by the 2. And as you can see, that gives us a final number of 1.265. Now, if we were canceling units as we go, we would see that moles of NH3 and moles of NH3 cancel, and my final unit is moles of N2, so my final unit would be mole of N2. And there's your answer to your mole ratio problem. Taking a look at one more problem using our mole ratio. If 3.86 moles of potassium reacts completely with excess water, how many moles of hydrogen would be produced? So we can see here we have 3.86 moles of potassium. That's my given. Reacts completely with excess water, so that's just extra information we don't need. How many moles of hydrogen? So my unknown here is my moles of hydrogen. So my given is 3.86 moles of K. My unknown is my moles of hydrogen, so I'm going to write in moles of hydrogen. So I see here I am going to go from moles of my known to moles of my unknown. Now we have a slight problem here. This is the first time we're looking at an equation that's not balanced. Pause the video, take a moment, and see if you can review how to balance the equation. Here's what you should have for a correct balanced equation. 2K plus 2HOH, which remember HOH is also H2O, makes 2KOH plus a blank, which remember is 1, and we don't need to write ones. So just like our stoichiometry problem before, we start with our 3.86 moles of our potassium, and we multiply that by our mole ratio. Now remember, our moles of our known go on the bottom, so that's our moles of our potassium. Our moles of our unknown go on the top, so that's our moles of H2. So I look at my coefficients. I see that there's a 2 on the potassium, so there should be a 2 here. I see that there's a 1 on the H, so that 1 would come here. I multiply across the top 3.86 times 1 all over 2. And remember, canceling units as we go. Our moles of K cancel. We have moles of H2 as our final unit. So 3.86 times 1 divided by 2 gives me 1.93 moles of H2.